Hey guys, it's Mr. Sheeline here. This is going to be a video covering how it is that we can figure out the distance, the velocity um, of a what we call a geosynchronous or geostationary satellite. So before we get into any kind of mathematical material here, what I want to do is I first want to break down what that word geosynchronous geostationary means. So just using the geostationary terminology that flipping physics uses here, um, the if we break down what geostationary, what geosynchronous means, if we break it down, we've got geo as our prefix. Geo more or less just meaning Earth. It means just Earth. Okay, I believe it's Greek if I'm remembering off the top of my head correctly. So geo means Earth. Okay, got it. Then we have to wrestle with the term stationary slash synchronous. So geosynchronous, geostationary for the most part means the same thing. It means that it's going to be a fixed position, the same position. So what does it mean to be of the same position as the Earth? Because if we put that together, that's what that would kind of translate into. Well, it would translate into what this GIF is showing us right now. Here we have a satellite right here. We have a satellite moving around the Earth. It's orbiting around the Earth. And if we notice real quick, this geostationary, this geosynchronous satellite is fixed right here, probably somewhere at the tip of Siberia. Okay, and it fixed itself to just this particular area, and it does not move. Okay, and so and this is a real thing that scientists have actually done and calculated. Obviously, if they've done it, but we actually do have geosynchronous satellites out there, and so what we're going to be doing is we're going to be figuring out just how far away and how quickly our object has to be, well, how far it has to be, and then how fast it has to be moving in order to stay in this geostationary, geosynchronous position. Okay, and a lot of these are used for like imaging. This is a lot of it's used for like direct TV. You don't want all kinds of different satellites bopping around and twisting signals. You want to have, and that's, you want to have a satellite that's fixed on one position where a connection won't be interrupted, relatively speaking, by really anything, or at least, but you don't want it to be messed up by anything interfering with it. So anyway, so we are able to calculate this, but how is it that we're able to calculate this? Well, before we can get into the calculations, some things we have to consider. So just remember that when we are going to be calculating this, we have to make two distinctions when it comes to this little r squared here. So keep in mind that when we are determining how far away from the Earth that these geosynchronous objects have to be, these satellites have to be, we have to keep in mind r is this right here. Okay, r is the distance from the center of the Earth to the center of our satellite. And in these questions, and you'll just have a couple of them, but for the most part, especially with these satellites, we don't care about, roughly speaking, we don't care about the radius of the Earth in this case. We want to know how far away from the surface of the Earth, really the equator, how far away from the surface of the Earth is it that these satellites reside in? Where is it from here? What flipping physics calls the altitude, from the surface of the Earth out to, away from the Earth. How far is this distance? And that's what we're going to be looking for. And so in order to find that, we can use these two equations for the most part we've already been using. Now, the only difference is that we have to understand exactly how to use these. So if we're working with a geosynchronous object around the Earth, it shouldn't be too difficult. So in order to figure this out. Now, we don't have to solve for the velocity just yet, and we'll see why, because really we don't want to solve for the velocity until we know how far away it is. But we have to then think, well, how is it that we can figure out the period of this, the distance of this thing, if we just, there's really not a whole lot of unknowns, because there's not a whole lot of known things. So things that are going to be known, well, of course, we have G in both cases. We'll have M. This should say M2 over here, by the way. Like, this should have a little 2 on it, and there's no black. This should have a 2 right here. So we have the mass of the Earth. Okay, in both of them, we have G, which is a universal constant. 2 pi, no problem. We don't have V. We're going to talk about this, and we definitely don't have this. Okay, because this is going to be R is going to be that radius. It's going to be the distance from the center of the Earth to our satellite. So there's a lot of things that we have, but at the same time, there's a lot of things that we don't have. So what can we do if we have all these unknowns? So let's think about it real quick. And go back to the previous slide. Just conceptually, we have an object that is moving relatively the same as the Earth. So, and remember, what is it? What is it that is happening here? We have a satellite that is on a fixed position of the Earth. So technically speaking, this is moving at the same rate as the Earth is moving. It's orbiting at such a way that it is mirroring. Or I should say, it's copying the period of the Earth. So when we are making our calculations, we can simply say this, that we actually have T. We have period. Now, the only problem is that for the most part, we know what the period is off the top of our heads in hours. So we know that the period, wrong color. Let's not do that color. We know that the period of the Earth, we already know that that's going to be, roughly speaking, about 24 hours. It's really, I think if it's 23.94 hours, but this is the period of the Earth, right? So, but if that's the period of the Earth, then it should also be the period of the satellite as well. Because again, think about it. If I can go back, if you think about it, the Earth, if you were to start right here, if you were to start if you were to start counting right here, and let's say that this is moving, we'll say at real time, when it comes back to here, it'll be 24 hours, the same as it would be for the Earth. So in order to make one full revolution around the circle, the satellite is going to take roughly 24 hours in order to or to travel around the circle. Makes sense, right? So the Earth rotates and makes a full rotation in 24 hours. And because our satellite's locked in one position, it's locked into one section of the Earth, it also will take 24 hours for one revolution as well. And so that then means we can use this equation to give us this guy right here. The only problem is that we then have to make some derivations in order to figure out what this is. So again, when we have geosynchronous satellites, the period of the Earth, period of whatever planet your satellite is orbiting, is going to be equal to the period of your satellite. Okay. Now, how is it that we can get this guy all by himself? Well, let's just kind of do this real quick. Well, we're going to, in order to do this, we're going to have to divide this guy to both sides. So then it's going to be T over 2 pi square. Okay, cool. Got that. Okay, well, then what? Here, I'll get rid of these just so it's not too confusing. Oh, and then what? Well, then we can see here that, well, there's a square root because this is gone. Okay, we still have the square root r cubed divided by big GM. So it looks like we got to get rid of the square root. So we're going to square root both sides. Boom. Boom. So then it's going to look like this. That's supposed to be a 2. Okay. Okay. So then that's gone. Okay. Then that's gone. We don't have the square root anymore. Don't have that. So now it's just r cubed over big GM. And then we're just going to multiply big G. And then again, it should be M2, M of the Earth, which is going to be equal to r cubed. Okay, so with me so far. And then if we got to get rid of this, it's just we're going to find the cubed root of everything. Find the cubed root of everything, which then will give us this. The distance from the center of the Earth, remember, to the center of the Earth, to the center of our object, our satellite, is going to be equal to this. It's going to be r is equal to the cubed root of the period over 2 pi. All of that's going to be squared times big G times m2, which is going to, in this case, in most cases, it's going to be the mass of the Earth. And we would use this guy right here, this derivation, in order to find the distance from the center of the Earth to the center of our object. And then when the question then asks us, well, what's the altitude? What's the difference from the surface of the Earth? We would just take this r right here and we would subtract the radius of the Earth to find out just how far away this particular satellite must be sitting. And then that's what we're doing. That is what we're going to, this is how we find out the radius of our geosynchronous object. Okay. And then we can also figure out, because then that r, now, well, not this r right here, we then can use right here. So this r right here is the same as this r. It's from the center of our object to the center of, it's the center of our Earth to the center of our satellite. We can use it here to figure out just how quickly our satellite is moving relative to the mass of the Earth. Okay. So that's how it is that we can find geosynchronous objects. I had one other point, and I'm trying to remember what that point is. And I forget. If we don't know how to, let's see, Texas Instruments, or no, just TI. Oops, TI-84 calculator. So if you want to know how it is that we can, how you can find the cubed root if you've never found the cubed root before, all you need to do is this here, and I'm going to drag this image onto here. So if you've never ever done this before, which I'm really hoping you have, it's kind of weird, junior, senior year if we haven't, but just in the case that we haven't, or we just forgot, if you've got a TI-84, what you're going to do is you're going to hit this button here. Oops, I don't want that. You are going to hit the math button right here. And once you hit the math button, looking at my own calculator, you hit the math button, and then you will be given a number of different options. The first option is going to be fraction. Second option is decimal. Third option is cubed. And then the fourth option is cubed root. It'll look like this. It'll be like a little 3, and then it'll have like the square root symbol, and then with a parentheses in it. This is what we're looking for. This is what a cubed, and really this 3 is a little off because it's like a little 3. It looks a whole lot more like this. Okay. This is the button that we're looking for, and that is what you're going to use in order to find the cubed root of whatever we need to find the cubed root of. So that's pretty much it for this video, guys. Again, this is something that I went over in class, and I really do hope this helps you out. If you were in class and you just kind of forgot, hopefully this will help you out here. And that's it. So if you guys still have any questions for me, make sure you ask. If you were absent and you were not in class the last day before spring break, I hope that you have a really fun and safe spring break. Take it easy. Don't go too crazy, obviously. And I will see everybody back, and I mean everybody back, when we get done with spring break. And if that's all it is, and if you don't have any questions for me, guys, then I'll see you in the next one.